All right. Hi, I'm Jesse Wilson, and I'm going to be talking to y'all about Coroutines party tricks. Um, Party tricks. Coroutines are neat. We can build lots of cool stuff with them. You can also chop your head off with them. And I've got 10 different, just like silly, fun things to talk about with coroutines. And I just want to sort of like nerd out and get excited about coroutines. And so I'm just going to go rapid fire, hopefully have a lot of fun. So first one is IO. I've actually got four IO coroutines party tricks, and then I got some navigation UI party tricks at the end, and then some bonus ones in the middle. So everybody is like, yo, why does our IO libraries just not natively suspend everywhere we should do them? And so if we go back through like the history of coroutines, Kotlin X IO, the very first version, not the current one, it was suspending an API. In 2018, we tried to do coroutines in OKIO the first time. Ktor still sort of like got the CIO thing that's coroutines. Brian Norman, who gave the excellent talk today on Magic Move, attempted a coroutines version of OKIO, and we've just continue to get coroutines ideas. And so like, let's just do it and see what happens. Do we chop our head off? So I'm going to take the OKIO buffered source interface and I'm going to focus on two functions. Require, which says I demand that this source has 10 bytes. If there's not 10 bytes, explode. And request says, hey, is there 10 bytes? And it will say, basically, it'll block until either there's an EOF or until that 10 bytes is available. And so we're going to just take that API and we're going to rewrite it with suspend and see what happens. When we add suspend to any of the functions in OKIO, we sort of have to make it also happen in the functions that it calls and the functions that call it. And so for this experiment here at this talk, it ends up impacting, I changed about 300 functions in OKIO to have a suspend modifier on them, and about 200 functions in Moshi. And so our benchmark is, we're going to just get Zach Swear's excellent JSON parsing benchmark, and we're going to run it in blocking mode. And then later, we're going to run it in suspending mode and just compare the outcome. And the blocking one, we can parse JSON with Moshi at 500 megabytes per second. When we do it with suspend, it's way, way slower. It's about 285 megabytes per second. And like, we just added a keyword. It should not slow us down this much. And so I want to dig in and figure out why. So let's take a look at the bytecode. Where's the answer? It's in the bytecode. Here is the function in the blocking version. We have this require function. I'm going to go through this function a lot. It calls the request function. So just say like, hey, I demand there's 10 bytes available. And it says, is there 10 bytes available? And if it's not, it throws an EOF exception. And so I'm going to take that function here in IntelliJ, and I'm going to do this awesome thing. I'm going to show Kotlin bytecode. I don't know if you've used this. It's amazing, but I can't read bytecode. I'm not Jake. So I'm going to take that, and I'm going to decompile it back into Java. I get the Java, and then I still can't read Java. It's not 1995. So I take that, and I'm going to copy it, paste it into a new IntelliJ file, and I'm going to paste all that. And then I'm going to convert that to Kotlin so I can get something that I can actually understand. I'm going to copy that back and put that in my slides. And now I've got the new code. All right, here's the new code. Here's the old code. Here's the new code. Here's the old code. OK, so I did all that work and nothing changed, right? The code is the same. That was a waste of my time and yours. Let's do the same thing for the suspend modifier. So I'm going to take that exact same function. I'm going to do show Kotlin bytecode. Decompile it to Java, and then I can take that Java, paste it into a new Java file, and oh shit, I've got like undefined types and weird stuff. Everybody just wait 1 second. Let me just clean that up. All right, it's all cleaned up. I'm going to take that Java, and I'm going to convert it to Kotlin, Command-Alt-Shift-K, get my Kotlin. Oh shit, again, I have to tidy it up. Everybody please hang on. I'm going to convert that into clean Kotlin. That was, many, many minutes of my life. And now we finally have the new version of this function. So this was before we had like the suspend modifier, and then I'm going to effectively desugar it. And this is what we get after. All right, so this is your code on coroutines, and this is your original code. Again, a lot, not very much. And so what the heck? The coroutines code, if I just drill into it, probably the most interesting thing, I graded out foolishly, but the function takes a continuation in its signature. So the original function just took a byte count. Now it takes a continuation called completion. And then in the function signature, there's an anonymous class being declared, which is the continuation. And so if the function ever suspends, it's gonna call this function to resume it later, and it keeps that state in a thing called a label. And then whenever the function it called returns, it will shove that in this result variable. And then when it does resume, it resumes by being called on this invoke suspend function. So that will pick this function up where it left off. There's a bunch of code to sort of like set that thing up. And then the sort of like actual state machine of the system is this big switch statement where we say, are we in the case before we've called the first suspending function? That's like the, if something. And we set this up, and this is going to ultimately call the suspending request function on that third line. And then that will either return, or it will continue and drop into the first case. Or we're going to be after that first suspending call, and then we're just going to cast the result. That function has to return a Boolean if it didn't return an exception. And finally, we sort of like end back where we started, where we're actually seeing what the original function looks like. And so that is the desugaring of our suspend keyword on one function. And so suspend functions are awesome. They do just so much for you, but also they put a lot of work for the CPU to do. And so when we are thinking about stuff like OKIO and should we just suspend everywhere, we're putting a dramatic amount of extra work on OKIO. So my advice for you all is ignore what I'm saying. Like, don't worry, don't panic. Suspend is fast, but OKIO is weird. It is extremely performance sensitive. Almost all the code that we write day to day isn't going to have this problem. All right, dynamic proxy. So this one is the same situation, but we're way up in retrofit, and I kind of want to just talk about how coroutines and Java and this magic interact with each other. This is what retrofit looked like, in their early days, and then retrofit is older than Kotlin. Even the very first versions of Kotlin are old. Retrofit's older than those very first versions. In retrofit 2.6, we added an optional compile-only dependency on coroutines. But our Java users, who we really, really cared about in 2019, they don't have any Kotlin runtime dependency. The way that retrofit is able to support coroutines despite not having that dependency is we just don't have any Kotlin. We don't take your suspend function and rewrite it in Kotlin. Instead, we use this Java dynamic proxy feature, and it's super cool. It's like a really interesting, weird JVM thing. You call this function new proxy instance, and you pass a class loader. Hi, I love class loaders. Like, what the heck? And critically, that array is an array of interfaces you want to dynamically implement at runtime. And finally, an invocation handler. And so anytime you call any function on any of those interfaces you claim to implement, the invocation handler will get called, and it gets a function signature like this. And so we can take our GitHub service, we can add suspend, and then everything sort of like to make that suspend keyword happens inside of our retrofit invocation handler. So this is the whole thing. We're just going to implement that invocation handler interface. The invoke is the same, and then it sort of starts out all normal. We're going to call OKHCP, and then this is the sort of fun part. The very last argument for your retrofit call is a bonus argument. It is the continuation. And so when we compile Kotlin with suspend modifiers, it always adds an extra parameter, and that's our continuation. So we take that, and then we call a Kotlin suspend function from Java. Normally, you can't really call suspend functions from Java because you don't have a continuation. But hey, look at this. In this case, we do. And so in this case, we got Java and coroutines playing together. It's something you'll rarely see, but it's what makes retrofit work. There are some gotchas, like there's some dark magic happening where we're boundarying between these two systems. In particular, Kotlin doesn't really care about checked exceptions, and Java really cares about checked exceptions. So if your function throws Java will wrap it in this thing called undeclared throwable exception. And we work around that in retrofit by forcing a suspend, which is a really gross and weird thing to do. Fortunately, it's already done for us. My advice, this is like the big payoff from the previous trick. When we suspend in retrofit once, you don't have to suspend in OKIO for every single byte you read or in Moshi for every single JSON object you read. All right, I got 8 more to go. I'm going to continue this pace. All right, so I said 3 different I/O ones, and next one is going to be called cancel safely, and we're going to talk about OKHTTP. Here's a HTTP-like API, and it's only got synchronous calls and a callback. It doesn't have a suspending mechanism. The HTTP call is sort of like old school. And what we want to do is build a suspending overload of our HTTP call because we got lots of Kotlin users. And so the first attempt at this is we're just going to take that function and we're going to use the excellent suspend coroutine function that allows us to bridge suspending code to blocking code. And so the way this thing works is we get past a continuation and we have to complete that continuation when our callback happens. And so we'll implement our suspending code on top of our callback code. So we do that. And then when the callback actually happens, we'll say continuation, basically complete with this value. And that basically causes this entire function to effectively return that response. When it fails, we say, throw this exception from the initial function call. And unfortunately, this code is broken. If you type this in and you run it and you cancel that coroutine at any point, it won't do anything. So if you're making a 10-second network call, your 10-second network call will continue to run long after you suspended it. And so this happens in libraries like Coil, where you're showing lots of images. You actually want to make it so that if you've decided you don't want to load that image after all, you shouldn't have to pay for all the network bytes. All right, so the fix for this is really trivial. There's a suspend cancelable coroutine. Problem solved. All right, we use that. And this one is also broken, but for a completely different reason. Now the coroutine will return immediately if we cancel, but the HTTP call and the network is now still being wasted. So it's going to still do all the work and eventually call our callback, but that callback is just, nobody's going to answer. So finally, we add this invoke on cancellation call. And this says, if my coroutine gets canceled, here's some cleanup that I'd like you to do. All right, problem solved. Hooray. Isn't that cool? You just need to know this API. Oh, actually, I screwed it up one more time. The last piece is tricky here. In our successful case, we pass a response to basically the continuation. We return that response. And that response, in OKHTTP at least, is a live object that needs to be closed. And so in this case, there's an overload of the resume function that says, if before you deliver this response to the caller, if I get canceled in that case, here's how to tidy up. And that solution actually works. This is kind of hairy, weird code, and it's particularly difficult to test. But if you are using coroutines and cancellation and you're canceling I/O things, you have to write all this work. All right, stacks. All right, so this one's really fun. We're going to step out of I/O and just do some real sort of functional fun programming. I want to write code that's going to parse the expression on the left and return the value on the right. So I got the string 3 is going to return 3. The string 3 plus 3 is going to return 6. And 24 threes will return 72. And I'm going to write some code that makes this happen. This is really sort of fun. I don't know. This is the kind of fun code that you don't get to write at your job very often, but you do get to write if you're building a slide deck. So we're going to read the string out of a OKIO buffer. And we're just going to continue to consume characters from that buffer and evaluate as we go. So, first thing we do is just, read one number out of the buffer. If there's nothing left, we're done. Otherwise, read an operator like plus or times and recursively call with our value that we have in hand. And so I'm going to take that code. I'm going to write some tests for it. First test, perfect. 3 is 3, and 3 plus 3 plus 3 equals 9. And then I'm going to write a fancier test where I'm going to build a string that's 1,234 characters long or 12,000 characters long. And we'll run that one. and we get a Stack Overflow somewhat predictably. And so far, I haven't talked about coroutines in this trick, so let's think like coroutines. We got a recursive function call here, and we want to fix the code, and we're in the coroutines talk, so let's just coroutines this thing and see what happens. It still fails. All right, anybody got any more ideas? Because I got a really dumb one that shouldn't work. All right, how about we do this? Let's add a yield in the middle of our function for no reason. All right, and now I run the test, and I got a green passing test. Isn't that amazing? I think you guys, if you want to make your code more robust, put yield statements in, and it will fix the problems for you. It works because every time we call a function, even recursively, it pushes a stack frame. And when we yield, it just happens to sort of as a side effect, clear the stack or shrink the stack that it's using. All right, but there's one extra thing that you might have noticed here. When we ran that test, that took 2.5 seconds, it took 2 seconds. That was weird, right? It was really weird. So because I'm a scientist, we're all scientists, I'm just gonna like poke at this a little bit. Let's multiply the number of elements that we're gonna add by 2, and then we're gonna run it, and it turns out that the amount of time it takes to execute multiplied by 4. Huh? You know, I got our hypothesis is forming here. Let's quadruple the original size, and it turns out that the time it took to execute multiplied by 16. Huh? It's fun, right? Something's happening here. Now I'm going to run that exact same thing, but I'm going to run it in the. I'm going to run it normally. I'm going to run it normally. Usually, when I run my code, I run in the debugger. It's just sort of like where I live. But because this was weird, I'm going to run it just normally, no debugger. And it turns out, without a debugger, code's still super fast. So something is interplaying here with my super recursive function and my super recursive function and the debugger. And I don't know, this is like just something I discovered in the process of setting up this talk. IntelliJ is synthesizing stack frames for us, and that's a very reasonable thing for it to do. This only happens when you run in IntelliJ in the debugger, and it's not a performance problem in practice, but it was a really neat little thing to find. My advice for you all, if you remember the previous section where I said, add a yield function randomly to your code to like, antagonize your coworkers, just don't do that. You'll go to programmer jail. But there is a Kotlin feature called deep recursive function that does this in a way that's like very obvious and semantic. All right, I want to talk about sequences, and to illustrate this, I'm going to go back to I/O, my sort of happy place, and we're going to scan the file system. Maybe you want to just see like how many files are in your home directory or something like that. I want the scanning function to be recursive, visit every folder and then visit all of its children recursively. I want it to be streaming, so I get results immediately. I don't have to wait for the entire file system to be scanned before I can start operating on those elements. And ideally, simple. So to compare Kotlin's excellence with Java, I'm going to call this existing API from the Java thing, and it is beautiful to call. It's files.walk with a path, and it's a beautiful thing because I can break out of this loop whenever I want, and I can just recursively visit. I don't have to write any recursive code. I don't have to write any visitor patterns. It's wonderful. But if we look at the implementation of the Java code, I cry a little bit for the poor Java engineers at Oracle who had to write this. There's a deck. See that array deck thing? They have to manually manage basically a stack for where they are in the traversal, and then they have a directory node. So they have like a full computer science problem to solve of like how to make that beautiful function work simply and incrementally. So that's a lot of code in order to implement this simple feature. And some of that code, I'm being a little bit unfair. It supports symlinks, it supports streaming directories, which is like very exotic. But again, it needs like lots of computer science to work. Now I want to just absolutely hype Kotlin's excellent sequence API that we're not using enough. So this one, exact same sort of user interface, list recursively. And the implementation, are you ready for it? Here it is. That's the whole thing. All right, so now we use this this thing called the sequence builder. It's a little bit like build string or build list, but in this case, it's a sequence. And then we, do the sort of first step where we recursively collect. And then on this function, there's a very weird signature here. It's a suspend function, and the receiver is a sequence scope of path. And so we call that, and we yield this path, and then we can recursively visit all the elements. This one is just like beautifully simple. It's almost like a poster child of how excellent the sequence API is, because like that manual like stack and that manual, like all that extra data structure computer science is happening, it's still there, but the compiler is doing it for us, and it's doing it all for us sort of like automatically at build time. One other thing I want to sort of call out about this is that that sequence scope is not the same as any sort of like normal coroutine function. It's got this restrict suspension annotation on it, and you can't just write sequence anywhere and do coroutine stuff. It uses the suspend modifier, but it uses it in a very narrow way, and the only thing you're allowed to do is yield. So we've got sort of like two different language features, both built on the same suspend technology. We've got like regular asynchronous coroutines, and then we've got this generator thing. My advice here on this trick is, even though the old yield that took no arguments is forbidden and you should never call it, this one's awesome and you should call it all the time. You will not go to programmer jail. All right, now I want to celebrate some of the internals of coroutines. And I want to start by celebrating something completely unrelated to coroutines: hash maps. Everybody loves hash maps. We use hash maps every day. What is your job? Well, I kind of like manage hash maps. That's like what we all say as programmers. Hash maps are great because they've got a brilliant API where we just store stuff by a key, and the performance is fantastic. You don't have to think like, what data structure should I use? Am I going to put 5 elements in my hash map or 5,000? I want to just like go through a little bit of the computer science of hash maps, mostly because I love them. And so the mutable map and map of functions in Kotlin are implemented in the hash table computer science data structure. So we got like the Kotlin classes that are like our beautiful APIs, and then we've got like some hard computer science from like the 1950s or 1960s that make it happen. The way the sort of key insight of hash maps is that every value has a hash code that returns an int. And if two values produce the same int, if two values are the same, they definitely produce the same int. But if two values are different, they probably should return a different int. You could, like, it's legal to make a hash code that always returns 0, but you will not be happy. All right. So, and then the reason that it all works is that when we want to say like, find me, find me the mushroom in my hash table, we sort of use this hash code to jump to the right location in storage, and we sort of find our result immediately. Just to like hammer this home, I want to like open this up in my IDE. I've created a hash map with 2 elements in it, and I just want to look at it. If you right-click on a map in IntelliJ or Android Studio, and you view it as an object, you can actually see the Kotlin hash map implementation details. And so I can take that table and look at it, and it's full of nulls, right? There's just a whole bunch of slots ready for new values to be inserted. And then I scroll down, and at slot 8, there's my ham, and at slot 13, there's my mushroom. And then at each of these slots, there's a hash map node, which is an extra sort of additional data structure. I didn't have to ask for a node or create a node. It's just an implementation detail of the hash map. And that has a hash, my key h, my value ham, and an extra thing. And so in memory, I'm going to start out with my empty hash map, and I got like, create my map, it's empty, I got 0 elements in it. When I put the first element in it, I'm going to allocate a string or 2 strings on the heap. And you'll notice that sort of initially strings on the heap in Java have a 0 hash because the hash hasn't been initialized yet. Nobody's needed the hash, so we haven't bothered to do that work. But every string has a hash property in it, whether you use it or not. And then the very first time I call put, it will lazily create an array of 16 elements. If I put enough, it will eventually grow this array. And then it will compute the hash of the key. So it went from 0 to 77 here. And then it will create an entry using that hash code, link everything together, and then using the position derived from the hash, I think it's like just like the mod of the hash table size or something, it will put it in the array. All right, so that's great. When I add a second element, you just repeat the same process, and you sort of like hope that there's not a collision if there's not something else already in that slot, but if there is, that's what that next field is for. All right, so that's sort of like how hash maps work, and the reason I did all that work is because I actually wanted to talk about how efficient they are. When you have a hash map, you're sort of allocating a hash map object, the array of entries, an entry object for everything you put in the hash map, and then all of our classes in our Kotlin programs have extra fields just to support the case that they could be used in a hash table. And then we're also paying for it with memory, and we're also paying for it with CPU time. Every time we get an element from a hash table, we access 4 objects, and so it's not nothing. It's very close to nothing, but it's not nothing. And when we compute the hash the very first time, it needs to traverse the entire key object. In this case, my keys were very short strings, but in practice, if you're hashing large objects, it has to do a lot of work. And then there's extra garbage collection happening. So every single hash map we create, every single time you put, you're creating work for the GC to do later. This is not intended to shit on hash tables. They're fantastic. But it is a thing that coroutines implementation details are weird and extremely performance sensitive, such that using hash tables in the internal implementation details of coroutines would be very bad, and you would be able to see it when you run your programs. You would say like, oh, don't use coroutines because they allocate a lot of things, and that those allocations cost. And so I want to talk about how coroutine context gives us the great taste of hash maps with none of the calories. And so if you look at the coroutine context interface, it's got these 2 very hash map-like functions. It's got plus and get. Plus returns a new object. It doesn't mutate in place, which is different from Java's hash map. And in this sample, you can just see it like really sort of reads like a map. I can put 2 keys in and then read one out. I do have to do a lot of work to create my entry that I'm going to put in. You can't just put any object in a coroutine context. But if you create something that implements coroutine context element, that just defines that key operator, then you can use coroutine contexts. There are 3 different implementation sort of categories of coroutine context. First one's trivial. It's an empty coroutine context. Whenever you start, it's like creating an empty map in practice. Then there's a bunch of different ones that have 1 element in it, and that 1 element is the only element. It's like the self element. So if you have like a coroutine dispatcher, it acts like a single element map where the only element is itself. That's kind of weird. And then there's a special container type called combined context that combines any of the other 3. So you can have, you start out with an empty coroutine context and you add something, you'll get that something back, and then you add something else, and you'll get a combined context of the 2 things you added. And just to hammer this home, I'm going to actually walk through it. Again, we start with an empty map. Then we're going to add mushrooms to our thing, and we're going to create a key object to wrap that string, and a topping object that sort of acts as our entry. That's the thing that we're putting in the map. And then when we do the assignment, it just puts the map object pointing it at that 1 singleton map that contains 1 value. If I want to put another element in the map, we get that other element. I create a key for it and an object for it. This is the actual thing that we're putting in the map. And then when I call the map.plus, this is where the magic happens. It's going to create a combined context, and it's got 2 properties. Left is everything we've already got, and then element is the new thing that we added. And so now when you put or get on combined context, it can just sort of recursively say, is it in the left side, or is it the element itself? So that's if I wanted to do 3 elements though, this is where you can sort of see how this pattern starts to fall down. So I'm going to add a 3rd element. First thing I'm going to do is I'm just going to put everything over here to the side. I'm going to create my 3rd value, pineapples. I'm going to create those things, and then I get a 2nd combined context. And so when you build these things, you sort of see that they're sort of recursively built on each other. And so in use, it feels like a map, but the implementation is actually a lot more like a linked list. And so when you ask for something out of your coroutine context, it recursively visits every single one of those things. But n is very small in practice. I think n is typically going to be 1, 2, or 3 or something. So I just want to talk about 3 more optimizations in this excellent data structure. The first one is that like this is what I showed you because I want to like do a pizza joke, and we have like the sort of like pizza coroutine context. But in practice, the keys are not going to be like objects that have pointers to other objects. They're just singletons. So in practice, the keys are going to be things like coroutine dispatcher.key. That's a singleton object. There's just one object in the entire heap, or job.key. So the keys, there's like no extra allocation for your key objects. And then the values are the same objects as the entry. So like the coroutine dispatcher and the job, when I put them in a coroutine context, the entry and the coroutine dispatcher value are the same object. And that's why you have to implement coroutine context dot element whenever you want to put something in a coroutine context. And then the last optimization is that the coroutine dispatcher is like the most important element in this collection. And so there's special cases in the implementation of this thing where it will always put the coroutine dispatcher at the head of the linked list. So it will always visit this one first. It sort of always visits sort of end to front or right to left. And so that gives it really good performance. The memory overhead, there's basically a bunch of combined context whenever your thing gets big. And the compute overhead is going to be basically walking that linked list of combined contexts. The thing I just like want to celebrate is that coroutine context is thoughtful and fast. And I don't know, it's really excellent to be a Kotlin developer because we've got these types of optimizations where our programs are just sort of like fast for free because somebody really went hard on like tuning this thing. All right, I got 4 more. I'm going to fail gracefully next. So try catch, totally rad. We expect some operations to fail. Error handlers are also rad. So when you build a coroutine context, you can put a coroutine exception handler in it. And then if you ever forget to catch an exception, this thing will get called instead. A thing that I found, though, is that it's really hard to remember to universally add a coroutine exception handler every single time I create a coroutine. Maybe I forget, maybe it's third-party code. And so in Java, there's a similar type of problem where they have this thing called an uncaught exception handler. And so you can say every thread assign an uncaught exception handler if you throw and nothing catches it. Or there's even a default uncaught exception handler that's a global singleton for the process, where if somebody doesn't catch something, you can recover from it rather than like crashing your process. What about Kotlin multi-platform? Nothing. Unless, all right, so there's a secret function. Nobody's allowed to tell anybody at JetBrains that I did this. You can call a function called ensure platform exception handler loaded. And what this will do is it will install a global uncaught exception handler. You need those extra annotations, invisible member and invisible reference, to sort of like break all of the rules of visibility. This is not a function you can call normally. You have to basically take the key checks off. Using internal APIs like this feels bad. It's dangerous. You do this and then you try to upgrade your Kotlin version and something breaks. If you want this particular feature, and I promise you do, there's an issue to vote up. And even though all of this feels bad, crashing hard when your program throws an uncaught exception feels even worse. So I'm like, I sleep at night. All right, so now I'm going to do my last section of 3 navigation things. And this is like the most adventurous part of the talk. So your server is a function. We're very comfortable treating our server as a function. You pretend some remote API is a function we can call. You take a request object, we encode it as bytes and transmit it. We await the server to return a response. We decode that response and return it. It's not a perfect abstraction, but it works great. All right, but what about your user is a function? All right, so let's pretend I will have some decision. What do you want on your pizza? I encode it as pixels, and I show the user. The user clicks on ham and pineapple, and then they click the submit button, and I take that thing, and I've got a pizza picked out. Here's an example of an API where I'm going to just sort of hammer on this point. I can take a pizza REST API and say that the HTTP body is a parameter and the HTTP response is a return value. Or when I call it, it's just retrofit. It's very simple. It returns a service decision. Now I'm going to do the same thing for my customers. I'm just going to say I've got a composable function that has on result. My the data that I'm going to pass into my composable is a parameter, and the callback that will pass when it happens is a return value. And now I can call my user like they're a function. And in this case, I got some presumed API called display.show, and it suspends while the user's making the decision. But like, why? And I'm going to try and make the case to y'all. Abstracting a server and a function call makes sense. It's software, but abstracting a person is just a party trick. All right, so the real reason is that our applications are not just built of a single screen. So I'm going to show my pizza screen, then I'm going to show a confirm screen, then I'm going to show then I'm going to call my server. You say like, get me this pizza, and then I'm going to show a success screen. And so that's what this flow looks like in my UI. And so I got multiple screens. Now I want to change it up. I want to add a new mechanism. Maybe I want to upsell an extra pizza. So in this case, I just changed the business logic of navigating through my screens. I still show the get pizza screen first, but then the confirm screen, instead of just always returning a constant value, I can return either the user's chosen to add another pizza and we loop, or proceed and we go on to the next screen. And so I've written a navigation logic as a while true loop. I want to contrast this with like what we currently do for navigation with things like the Jetpack navigation. Instead of configuring a graph of individual navigation nodes, we just write functions that call screens. In the navigation system, when screens return values, it sort of like happens outside the system, whereas if the screens are functions, we can just return what the user chose. Nav controller is extremely flexible, and that flexibility is good when you need it and very difficult to understand when you don't. Whereas I think that having functions is like strictly structured. There's no go-tos, whereas every single navigation API has something that's like the go-to. I heard go-to was bad. And navigation controller, you can't really test those locally, but it's just function calls. This is what the sort of navigation API we built for this demo and for other things looks like. And maybe I don't want you to go away and throw your navigation code away, but I think that a thing that Coroutines can do that's really powerful is just model business processes directly without building additional data structures and things. I'm going to extend this idea a little bit more and talk about navigating back. So we're going to support the back button using coroutines. And so our hypothesis is the call stack is the back stack, right? That's already weird. We've talked about recursion a lot. And so I've added an extra show function that takes a block, which is everything that's going to happen that can go back to the screen we just showed. And so now, in my default function, if I call back, I just go back to the screen. With this, I can say, nest the screen I'm calling. And now if you press back on that confirm screen, it returns to the preceding one. And now I've got a very fun demo. So I'm going to start out by just walking through my code. OK, I've got my pizza picker. I'm going to add it to my order. I'm going to pay. And my pizzas are on the way. This is actually kind of a crappy demo because I've only got 3 screens. So I'm just going to stop doing the work and make one more screen. I'm going to do display.show get delivery screen and pass in my pizzas I'm delivering it to. And that is going to give me an address. And then I'll pass that address to the screen I'm navigating to. Save that. And then when that's ready, I'm just going to rerun my application now. So I've got one screen, pick my pizza. Second screen, confirm it. Third screen, this is new. I'm confirming the address. And then my last screen. And oh, hang on a second. I screwed up. I'm intending to show you the back button, but this is accidentally an iOS simulator. Sorry, everyone. All right, let's do that again. All right. So now we got an Android tool. So we're going to do that. 1, 2, 3. And now if I go back, it goes back to the home screen. Or if I start on the second screen and I go back, it goes back to the wrong place. And so I'm going to change that up a little bit. I'm going to say that the display function is just going to navigate here. I have to rewrite this code in kind of a weird way. Pizza. All right, and I compile. All right, and so now I'm going to demo this the same screen. So I'm going to start here. I'm going to go to my confirm screen, and now when I press back, I go to that screen instead. Isn't that cool? So just again, call stack is the back stack. All right, and the way that this works is that we run a Lambda in a job using async in that extra block that we pass in. When the user presses back, we just cancel whatever's happening there. And we can recover from canceled jobs by just showing the previous screen. Again, I don't know if you want to change your navigation story, but like you can just take real things and map them to coroutines. I got one last trick. I'm running over time, so if you all will stand up, that's fine with me. I want to detect idling. So if in my demo you saw that I showed like a spinner when we were calling the server, what if I want to do a different transition when instead of showing a screen, we're doing a like a network call? So in this case, I've got a simplified version. We're going to do 4 shows in sequence, and I want to make it so that when I go from screen to screen, it's just like a push transition left to right. But when I go from screen to spinner, it's going to fade to the spinner, and then when that spinner finally completes, we'll finally do the push. And so there's a little bit of complexity to make this sort of navigation magic work, where we're integrating the network calls and the navigation calls into one system. The way that we're going to do this is we're going to detect when my coroutine is suspending. And when we detect the coroutine is suspending, it's probably because it's doing a network call or a database call or something like that. Critically, when the coroutine is suspending, we know that another navigation event is not happening immediately. And so we just need to say, how do we hook this up? And the key insight is that the coroutine dispatcher API gives us just enough visibility into the internals of the system where we can suspend and resume. So our strategy is going to be, we're going to decorate coroutine dispatcher. Every time something gets enqueued, or every time a runnable gets enqueued, we'll increment the enqueue count. Every time something completes, we'll increment complete count. And when they're the same, we know that the dispatcher has no work to do, and we can fire an idle callback. So again, here's that same thing, sort of like in actual practice. We create our custom coroutine dispatcher. And critically, I'm not building an entire coroutine dispatcher. That's way too hard. All I'm going to do is delegate to a real coroutine dispatcher that does the real work. And all I'm going to do is decorate it, make it do the work. And then in my dispatch function, all I want to do is just call that block immediately, right? I just like delegate. And then everything else that happens here is just my before and after hooks. So I'm going to keep track of enqueue count and dequeue count, or complete count. When I dispatch a job for the first time, I'm going to increment that. And then when the job completes, I'll increment complete count. And then if everything that's ever been enqueued is complete, then I could call my on idle callback. And so this is what it looks like to use it. I take the coroutine context out of my scope. Then I add the idle callback. And then I can just start working on that. And in this case, the lambda after on idle callback is fired every time my coroutine suspends. There's a couple gotchas. If you do this the first time like I did, you can have it so that your callback itself does coroutines work, and then that will eventually complete, and then you'll call your callback over and over again, infinite loops. And then there's another gotcha, which is that there's a special interface that some coroutine dispatchers implement called delay, and you need to implement this interface for your tests in your basically your tests with the coroutines testing library to properly implement delay where you don't actually delay with real clock time. So advice, I don't know, the decorator pattern is powerful. You can decorate core framework types if you want. It's a little bit sketchy, and then you should watch out for internal facing APIs like delay. So those are my 10 coroutines party tricks. Coroutines can do a lot for you. They're fast, not free, but fast, and like there's tons of details in them that are really thoughtfully optimized. And don't go to programmer jail. Thank you.